All right, we're ready to start talking about our first technique of integration, and this is called substitution. Now, to motivate this, let's consider the following example. Let's evaluate the indefinite integral of 2x cosine x squared dx. Now, what makes this difficult to integrate are two things. First, there's multiplication, specifically multiplication between two non-constant functions, x and cosine of x squared. We don't know how to deal with that yet when it comes to integration. Second, we have function composition. Cosine of x squared is the composite function of cosine and x squared. Again, we don't have any rule that tells us what to do with composite functions. Now, where does this possibly come from? I mean, when we're trying to evaluate an indefinite integral, what we're saying is find a function whose derivative is 2x times cosine of x squared. So what we should do then, maybe, is think about what rules would we be applying in order to a function in order to end up with a derivative equal to 2x times cosine of x squared. And there are two things that I think about. First, that there's multiplication. It makes me think about the product rule. Second, that there's composition going on. Makes me think about the chain rule. Okay, let's take a look at these guys. So first, the product rule. Well, with the product rule, we end up with the derivative of a product is the sum of these two products, f prime times g plus f times g prime. You might think that the fact that we only have one thing here and not two things here immediately discounts the possibility of using the product rule in cases where we have just a product of one thing as opposed to a product of two things. It turns out that we can actually sort of manipulate the product rule in a way where if we start with a product of two things, we might be able to apply a technique called integration by parts, which comes from the product rule. But the main problem here is that this doesn't tell me anything about composition. There's nothing helping me with respect to composition right here. So the product rule is not immediately applicable in any case. Let's get rid of that. Chain rule, when I take the derivative of f of g of x, I get f prime of g of x times g prime of x. Well, the thing to notice here is that first of all, the chain rule, when I use it, ends up with a product, so that deals with the multiplication, and also it deals with composition. The final answer has a composite function in it. In fact, notice this. The final answer has a g of x on the inside and g prime of x on the outside. We've got x squared on the inside here and 2x, which is the derivative of x squared on the outside here. So this suggests that this actually comes from the chain rule. Okay, let's follow this line of reasoning that 2x cosine of x squared is a function which is the derivative of some other function where we have to use the chain rule to evaluate the derivative. So if that's the case, let's try to match up pieces of 2x cosine of x squared with pieces of the chain rule. Now we're pretty much forced to have this inside function g of x equal to x squared. But that's nice because g prime of x matches up with 2x, which is the derivative of x squared. All we're left with then is what does cosine match up with? And on the right, we need to match it up with f prime. Well, cosine can match up with f prime. So if f prime is cosine, then f is an antiderivative of cosine. So let's let f be sine of x. Then we have our setup, which is g of x is x squared, f of x is sine of x. So the derivative of f of g of x, which is sine of x squared, is given by the chain rule. The derivative of the outside function sine is cosine, and we leave the inside function x squared alone. Then we multiply by the derivative of the inside function, which is 2x. If I put that in front, we get back the same exact function that we started with. So we just showed that the derivative of sine of x squared is 2x cosine of x squared. And from that we can conclude that sine of x squared is an antiderivative of this guy. In other words, the indefinite integral of 2x cosine of x squared dx is equal to sine of x squared plus c. Okay, so let's try to systematize this. If we see an integral that looks like the following, and note here that instead of writing f prime of g of x times g prime of x, I'm writing f of g of x, just slightly different usage of f here. But in any case, let's keep going. If I see something like this, specifically what I notice is that I've got a composition and the derivative of the inside function also appears as a factor of the integral, then what we're going to do is we're going to introduce a new variable u and let u be g of x. So that, using this Leibniz notation, du over dx is equal to g prime of x. Now, here's a place where I'm going to be a little bit tricky. I'm going to quote-unquote multiply both sides by dx, which cancels the dx down here and leaves me with du is equal to g prime of x dx. It turns out that this is valid underneath the integral sign. This is a completely valid thing to do. So du is this entire quantity here, g prime x dx. Then we have the substitution rule, which is often called u substitution because oftentimes you let u be this variable of substitution. It says that the integral of f of g of x times g prime of x dx is the same thing as the integral of f of u du. All we're doing is letting u be g of x, and then du gets to replace the entire thing, g prime of x dx, and hopefully this reduces us down to a single integral that we can attack. All right, so let's actually see this in practice. Let's actually use this substitution rule to integrate 2x cosine of x squared dx. Now, I would like to note that I know to use this technique for two reasons. One thing is that I see a product, 2x and cosine of x squared. That is often something that suggests that I should try substitution. And also I see composition. And really, when you see composition, substitution is more or less always the game. So these two things that I see tell me to use, or at least try, substitution. So the natural thing to try to do here is to let u be the inside function x squared. Then du is equal to the derivative of x squared, which is 2x, and don't forget to put the dx there. Now, if you like, you can rewrite your integral so that the 2x comes after the cosine of x squared, so it literally looks like 2x dx, but you don't really need to do that. What I like to do is this. I just like to say, okay, here's u, and this right here, 2x dx makes du. So then I rewrite my integral as cosine of u du. 2x dx becomes du, x squared becomes u. The only thing that's left over is cosine, which just gets to hang out. And then this becomes sine of u plus c. Notice we're integrating with respect to u. Now we don't care about u. I mean, I care about u, but we don't care about the variable u. We care about x. U is an auxiliary variable. It's somebody that it's like a subcontractor. Somebody gave us a contract to do something, we subcontracted part of the work for somebody else to come in and do, but at the end of the day, we're the ones who are the bosses, we're the ones getting paid from whoever ordered the work, So let's get rid of u and replace it with what it is, which is x squared. So we got sine of x squared plus c. Great.